Today's is going to be a little bit different. We are going to be showcasing a lot of innovative solar folks. And so we're doing this a little bit differently and innovative. Each person is going to have around 5 minutes to talk about their innovative solar design.
Yep, and we've got 10 solar companies that are talking. And after they are done with their presentation, we will ask kind of about the design cost, if it's more, less, or like kind of on a standard range. And then we will post this recording as well, just so everyone knows.
Okay, so we've done this all as one long presentation just to keep this quick. Okay, so we're going to start with Mo Horowitz from Solargik, and he's going to talk to us about the innovative agrivoltaic applications that they have there. Take it away, Mo.
Thank you, Stacy, and thank you for this opportunity. And as you can see on the screen, our focus in building our structures is really incorporating the 3 principles that you see here: smart, lightweight, and versatile. In a sense, our goal is to address what we see as really the 3 biggest challenges of Agri-PV: the ability to properly balance the sunlight between crops and panels, and be able to make sure that each side gets the sunlight that they need. We focus on creating a lightweight structure in order to enable the ability to install it in many places, whether that's above crops, greenhouses, other agricultural structures. And the versatility allows us more flexibility in terms of working with land contours and various weird shapes in order to maximize output and power density. Let's go to the next slide. So even though today's focus is on structures, I'm actually going to start here with a few points around how we actually make sure that we can balance the light, because increasingly for Agri-PV purposes, we are generally looking at dynamic structures where we are able to balance the sunlight and the shade between the crops and the panels. And what you see here is our ability to model and actually impact in real time the sun's path towards the ground or towards the panels. So in a sense, before designing and implementing a project, we're able to both create an agricultural model that tells us how much light is going to the crops, as well as a financial model that tells us how much of the sunlight is going to be used for energy generation, crucial both for the farmers in terms of making sure that they can hit their agricultural goals, as well as making sure that the investors, developers are able to get their financial plan approved by the banks if they're going to get funding for the project. Obviously, there's far more sophistication than this when it comes to managing this in real time, but this is more of a sense to give you that we aren't just focused on the hardware and the structure, but rather how we actually use it in real time, because that's really the main challenge of Agri-PV. Let's jump to the next slide. In terms of structures, we actually design a bespoke solution for Agri-PV that is very, very different from the traditional trackers that you see in the market. If you think about a standard solar field, you think big, long, straight lines, flat. And if you think about trackers, they're built for resiliency, which is great unless you need to put it 5 meters in the air and then also be able to do O&M and maintenance above crops. So we've actually designed a structure that is very different. It is meant to be lightweight. It is meant to be elevated above crops. We're purposely using smaller components and less steel in order to make the installation simpler and less cumbersome inside a big agricultural field. And we've designed in a few extra things that typical trackers won't have, such as the ability to flip the tracker upside down so you can actually clean it from underneath, something that is crucially important in an agricultural setting where you do have more dust and soiling than you would have in a typical situation. Another main component, probably similar to other photovoltaic settings, is that we are very focused on enabling a low LCOE, competitive pricing, competitive LCOE. So if we're elevating the structure, which typically raises the price, we're making sure to pull a lot of the steel out of the structure by making it more lightweight in order to maintain a cost that is relatively comparable to other forms of energy generation. How do we do that? Let's jump to the next slide. We are also able, by making our trackers shorter and having fewer panels per motor, that gives us a lot more flexibility in terms of where and how we can install it. So if we think about grazing settings, if we think about crops, orchards, or even potentially various types of other agriculture, we know that the terrain is not going to necessarily be an ideal terrain. Obviously, we want to avoid needing to do any type of expensive civil work or cut and fill. Clearly, we're not going to do that if there's orchards or vineyards underneath. So our tracker is designed to be much smaller, much shorter, not height, shorter, fewer panels. And that gives us flexibility in terms of installing it on the very different locations. And it gives us a lot more versatility in terms of where we're doing this. So let's jump to the last slide. And just to give our viewers / listeners a sense of what we're doing, we aren't just focused on one specific agricultural setting. We are building this in a way that really enables farmers to install this type of a solution any place on their land / field. It could be traditionally on the ground, like you see on the bottom right, where it's elevated. It can be above a dairy farm, as you see on the left. It can be on a greenhouse, as you see on the top right, and it can even be above fish ponds. There are actually many more settings that we can use, but this is meant to give the viewers a general sense of the versatility that we believe really needs to be added to these types of structures, because one size does not fit all. And we know that in order to really generate ideal returns, both from the agricultural sense and from the electricity sense, we really need to tailor this type of a solution for the specific setting. And that's a lot of the work and the research that we're doing, making sure that this can really fit in as many settings as possible to enable dual use of land usage and agricultural usage and solar energy generation. Thank you very much. And I will pass it on to some of the other presenters for today.
Thank you so much. We also did a follow-up question, Mo, and
Okay.
we could perhaps splice this in at that point, where we asked everyone if they could speak to the cost difference, how this compares to a standard solar install. Is it more or less the same?
Yeah. So should I just jump in and answer?
Yep, go ahead.
Okay. So that's a great question. And it's actually the main focus that we took into account when designing and building our structure. Because if we're just thinking about doing this on one farm here or there, or to be reliant on incentives, yes, we can design a really robust structure that adds 3, 4, 5 times the capex, and it will be beautiful on paper, and it won't actually get done in real life. So we understand that for this to scale, this is not that different to where the world of solar energy was, say, 5 years ago, until we hit grid parity. What happened when we hit grid parity? Suddenly, this just makes financial sense, and we see a hockey stick effect. We understand that in order for Agri-PV, agrivoltaics to pick up, the same thing has to be true. It cannot be solely reliant on incentives, and it has to make financial sense. That's why what we did is historically, the main cost of a tracker system was the motor. Once I had a big, heavy, expensive motor, I tried to put on as many panels as possible, 60, 70, 80. Most tracker manufacturers compete on how many panels they can add. We're doing the exact opposite. We're trying to use many motors, small motors, cost-effective motors, but that lets us pull out a lot of the steel. So about 30 to 50% less steel. So our agrivoltaic structures that you see here end up being roughly the same cost as your standard ground mount system. So our standard ground mount system is about 20 to 30% cheaper than the agrivoltaics, but our agrivoltaic structure, because it's using less steel, is actually at the same cost as you would see for a standard ground mount tracker, right? And that was not an accident. We understand that for this to really scale, the cost has to come down, so this can be cost competitive with any other solution on the market. I don't mean any other Agri-PV solution, any other PV solution on the market. So you can have an Agri-PV field on one side, and you can have a ground mount field on the other, and they need to be able to be similar in terms of cost. And that's one of the things we are working to improve and bring to the market. Thank you.
That's just great. Thank you so much. All right, I think that should do it, Mo.
We're gonna start off with Ian Score from Sandbox Solar. We just need to scroll down to their presentation.
Yeah,
Sorry about
okay.
that. Can everybody see that?
Nope.
Yep. Okay, and just let us know when you want us to go to the next slide and we'll scroll through. So just take it away, Ian.
I'm not seeing the slides.
Oh, you aren't? Okay,
No.
hold on.
Share screen.
How about now?
And then go down.
Okay,
Now I can see them.
all right.
Perfect.
The toggling.
Yeah.
Okay. And if Mo joins late, we can always come back to Mo's. Okay, so go ahead.
Hi, everyone. I'm Ian Score. I'm the CEO and owner of Sandbox Solar. We're a solar energy sales install professional in Fort Collins, Colorado. We've done everything between residential plus storage, commercial, microgrids, EV chargers, and we've been doing agrivoltaics since 2018. In 2018, we actually won grant funds to deploy the US's first semi-transparent research site at CSU, pictured here. And it's kicked off a few solar developments, which I'll share one epic one today. Next slide. Next slide. Awesome. From this research, we realized that developers need a tool to help farmers decide what can grow underneath the crops. And so using the Spade agrivoltaic design software, we were able to model the irradiance underneath the panels and show what kind of crops could have likely success underneath the panels. And we're working with NREL and others at CSU to determine other factors like water evaporation. Next slide. So using that model, we were able to approach a farmer and develop a solution for them to maximize their land use in Fort Collins, Colorado, where they didn't have any land or much roof space to install solar, but they had area between the greenhouses to install solar panels. So we installed a vertical bifacial solar panel setup between these greenhouses, and the farmer was super excited because the panels cast some shade on the edge of the greenhouses, which they thought would help reduce the edge effect of the greenhouses, meaning the water evaporation, yet let enough light through to continue to help the crops grow. Also, with the greenhouse film, we get a high albedo effect, and so we're producing high energy on both sides of the panel. And this takes place at Summit Plant Laboratories in Fort Collins, Colorado. Next slide. So here's another close look up of our team installing the solar panels mounted vertically, producing energy from both sides. Next slide. So you can see from a little snippet of a full sunny day, this is a 15 kilowatt system, and we're peaking both in the morning at about 9 a.m. and the afternoon around 3 or 4 p.m. So we get a double peak outside the normal typical boundaries of a solar system, which is incredibly unique and exciting. Also, we noticed that there's no snow soiling effect on the solar panels, meaning that the snow sheds right off, and we're producing way more energy from this system in the snowy conditions of Colorado versus the rooftop and other ground mount systems. Next slide.
Okay, next we're going to hear from Jake Marley at Hyperion Systems.
Hi, everyone. I'm Jake Marley. I'm from Hyperion Systems. Hyperion is a project developer and EPC contractor based in Western Massachusetts. In this presentation, we'll look at a few of the projects that Hyperion installed in its early days, which was the 2010 through 2012 sort of time frame. The picture we're looking at here is from the South Deerfield UMass Amherst Cafe Center, which is the Center for Food, Agriculture, Food, and Environment. This project was built in 2010, so quite a long time ago. It was brought about through a private sector, public sector collaboration, because at this time there weren't any racking solutions specific to agrivoltaics that were commercially available. So this is something, this racking design that we've used at a couple of sites. We'll look at a commercial, small commercial, and then a slightly larger commercial in the coming slides. That is similar to this racking structure. A couple of the details that I kind of wanted to point out. It's over-engineered. The company Hyperion's founder, Dave Marley, wanted this not to be an issue for the coming years. From 2010 through 2015, there were cattle grazing underneath the panels, which are elevated 5 to 7 feet. There's a bit of a slope at the site. One of the things that they found early on, or one of the challenges early on they had to overcome, was uplift. And so they installed this without any concrete. In order to do that, they increased the surface area. So these are 8-inch Schedule 40 steel posts, but they actually increased the surface area of the post by welding fins sort of at 90 degrees. So those are buried about 10 feet into the ground. Again, no concrete, so a lot easier site install.
Hi there.
And a lot easier to remediate at the back end as well. So this project has been a part of the NREL Inspire study, which is now in its 7th or 8th year. The crops grown, agronomist Dr. Steve Herbert from UMass Amherst has been in charge of that study. Hyperion was tasked with creating a financial model for Inspire 1 and was a part of Inspire 2 as well. The 4 crops that Stephen and his team have grown consistently are kale, Swiss chard, green bell peppers, and broccoli. And they've had varying levels of success. The drier years, 2017, 2020, and 2022, yields were really quite comparable to the control group, which was full sunlight. I think that's about it. A couple of the other unique things about this site, it was really set up as a research pilot project. So some of the parallel parallel spacing between the modules varies between 3 to 5 feet. So some of Stephen's studies touches on that, the different growing conditions. And you can also see, the last thing I'll point out on this slide is the shading of the panels. Throughout the day, that shade will really cast and change its variation, allowing for different amounts of sunlight. So those 3, 4, 5 foot spacing allows a little bit more insight for the researchers and just more data points. I think that's enough about this slide. We can go to the next. So this is a smaller site, 25 kW in Leeds, Massachusetts. I included this one. These are 4-inch Schedule 40 steel posts. So what they found at the UMass site doing some pull tests, that 8-inch was a little bit overkill, not to be too certain, I guess, the first time really trying this in 2010. This was at a family farm. The owner didn't want to lose any of its family garden space. This site services, it's a net meter project, so the power goes back to the grid, but it services his home and then his son's home, which is neighboring here as well. So it services their power needs. One of the reasons I wanted to include this is because of the drip edge. We can go back to the last slide, sorry. The drip edge. So that's something that at UMass they learned early on. Of course, there's a compaction point for any rainwater. So one, I guess, tactic that this farmer used, this grower used, is allowing the vegetation to kind of grow up a little bit here, not out of control. It's still, he's keeping a close eye on it, but it might be, it might, I guess, compact the soils there, but if you have to be mindful of planting is sort of what I wanted to highlight there. And if anyone on the webinar today has heard Byron from Jack Solar Garden talk about that, I think in a commercial setting, you might put straw down on those drip line areas. He's grown, so this grower has broccoli sets here, and you can see in pretty full shade. This is from June of last year, so he had probably just planted these, which is why they're small starter sets. But he's grown a variety of crops, squash, even watermelon, which is really a sun-loving crop. But he's had pretty good success, and we can move to the next slide. So this is a rendering of that picture, and I wanted to include that because I thought it offered a different perspective of the shade. This is, of course, south facing, so we're sort of at like the northwest corner, I guess, of the array. This offers some panel spacing, row spacing. You can see over in the left side, the panel height listed about 15 feet to the back edge, 11 feet to that horizontal piece, or what we would call, I guess, the spline. And then it's about 5 feet to the leading edge at this site. The front row, it's a little bit closer because there's a slope down towards the front. But I think that's about it on this slide. And I'm probably getting close to the 5 minutes allocated, but this is a site in Hadley, Mass. The owner of this array, this served power for some of his commercial businesses, and he hasn't grown anything directly underneath, but Valley Malt produces both in front and back of this array, growing barley, wheat, rye for their brewery production. This is a 100 kW array built in 2012, same racking design, a lot tighter panel spacing compared to the 3 or 5 foot. This was a commercial use setting, and I think it's worked out pretty well. So those are about 6 inches there. I'll yield the floor to James.
Thanks, Jake.
Yep.
Hi, everybody. I'm James McKinnon, CEO and founder of Helical Solar. We are based out of Leander, Texas. So we're a rural solar and agrivoltaic startup. Our additional funding has come out of U.S. Department of Energy SBIRs. We're also pleased to be part of the upcoming USDA Climate Smart Commodities Low Carbon Beef Consortium. We're going to install basically dual use inside of feedlots. So our product is a 4 meter high or 4 meter panel height bifacial dual axis tracking design. And it's unique because it doesn't have concrete or guy wires to install. We use a patent pending helical pile to do that with. And so we are targeting full-size livestock and row crops. And our business model is a little bit different than typical solar companies. We are trying to become a B2B partner with utilities, whether that's co-ops, municipalities, or IOUs. We also offer easy removal and recycling at the end of life. It actually goes out easier than it goes in. And we are seeking seed funding right now and paid pilot opportunities. Next slide. So our design consists of 2 basically easy to install modular sections, and we do that by using the ubiquitous digger derrick truck, which is found in every utility, regardless of how small or how large they are. So we install the helical pile first using the auger function on the digger derrick truck, and then we crane over the pre-assembled, pre-wired array, and that bolts in at the top, which provides basically a complete mechanical system. And then it's just a matter of some rudimentary wiring to finish up the install. So after arriving on site, we can typically do this in under an hour. So what we've tried to do is bulletproof the design. We have elevated electronics. Our cabling is all in structure and underground. We have about 136 mile-an-hour wind loading capability. And we use solid state sensors to actually detect when we need to go into stow for that. We can support about 10,000 pounds of snow loading, and we actually have active snow detection, so we can dump when we are at or around cold temperatures. And we do have 4G LTE backhaul, and we can support AWS backend and a remote shell capability to the systems out in the field. So this is our 3rd generation or our latest array. And this is a folding design. It's about 300 square feet in total array when it's flat as a tabletop. These are based on the latest M10 Tier 1 solar panels. Again, we have a 4-meter, 13-foot ground clearance for agrivoltaics. And this system has a 5.45 kilowatt nameplate. And when you compare it to a 7.72 or rooftop system, you get about a 7.72 kilowatt equivalent, which would generate about 10.5 to 12 megawatt hours per year. And so the key about this is this design has been optimized to offset the typical single family home consumption, which is around 10,900 kilowatt hours per year. Because it is a foldable design for transport, we can ship 4 of these on shipping skids, 4 per standard 18-wheeler flatbed. So we can deliver these things cross country to where either a field site or to the utilities for storage. So that's all I've got. I'm not sure who's supposed to go after me next, Daniel.
Yeah, Tim. Tim is supposed to go next from Sunzon at Sunstall.
Yeah, thank you so much for the introduction. Yeah, my name is Tim. I do the product management for Sunzon, which is the vertical solar system that we at Sunstall just launched last year. And Sunzon is all about dual use. So agrivoltaics is one possible application of this vertical system, but there are also other possible applications. If you think about, for example, the use as a fence for residential applications, or around parking lots, gas stations, carports, where you want to charge your electrical vehicles, or also applications that we're not even thought about yet, for example, next to highways or railroads or even canals. So that's why we call it Dream Vertical. But yeah, let's focus on the agrivoltaics here. And if you go to the next slide, then we can see the racking system from a closer view here. You see the bifacial panels and the posts that are driven into the ground, and also some of the dual use benefits of a vertical solar system. So one dual use benefit is, of course, the use as a fence for private property or livestock. But if you install this on a farm, you could benefit from some wind protection. So wind protection could decrease the soil erosion, which can be a real, a real benefit for a farm. And also, of course, there's shading, but the shading, shading for crops and laborers. But with this vertical orientation of the modules, it's a little bit special. So as Ian showed, the bifacial panels produce a lot of electricity in the morning and in the afternoon. But at the midday, the crops still have the full exposure to sunlight, just because of this vertical design. And also it's possible to harvest between the rows. For example, you could imagine like a couple of rows with maybe 8 meters row distancing, and then you can move your harvesters between the rows. So if we go to the next slide, then we can see, you can see it better here. So all the pictures that I showed you are from our first project on a winery that we had, where we installed the Sunzon. And you can really see how the system here just fits between the existing rows of the grapevines. And what we also learned with this system or this specific project was that agrivoltaic installations have specific challenges. So on this project site, it was really the slope to move the equipment here and to get it installed was challenging, but we made it. And we also learned that this vertical design with all those posts can follow the slope quite well and just suit the farm well. So the farmer was really happy that he just had to take out one of his rows of the grapevine, and then he could just have some solar panels right on his vineyard. And I think every agrivoltaic site has specific challenges depending on the crop or the animals that are on the farm, or the goals that the farmers have. So I think this also influences then which system will suit the farm the best. So the vertical system is our product. We call it Sunstall. And thank you so much for giving me the opportunity to present it here. I think it's really good to have webinars like this where we can learn. I think the AgriSolar Clearinghouse is doing a great job here. And to every farmer or solar developer, or everyone who attended this seminar and is interested in learning more about the vertical solar system or want to share insights about agrivoltaics in general, feel free to reach out to us. We're really happy to discuss. So thank you so much.
Thank you so much. That was great. Okay, David McFeeters-Crone is next, talking about RUTE and SunTracker.
Thank you, Stacy, and thanks to AgriSolar Clearinghouse for having this great session today. I've already learned a ton about some of the other foundations that are out there. I'm Dave McFeeters-Crone from RUTE SunTracker. What you see on this first slide is a rendering of our recently permitted project in Grant County, Oregon, that was unanimously approved through that process. RUTE has a number of unique applications, but we're really focused on cattle and rangeland. As you all know, there's a lot of impact on being able to do dual use, particularly with grazing, but frankly, there just aren't enough sheep. So there's about 10 times as much grazing land for cattle as there is for all other animals combined. And in fact, there's about 3 to 4 times as much cattle grazing land as there is for all the food that's grown in America. So there's a tremendous opportunity if we can just get the panels off the ground and have it be robust enough for cattle to freely enjoy the shade and the great forage that exists underneath it. Can you move to the next slide? Our technology has been funded in part by the DOE as well as by the USDA through SBIRs, as well as some private funding. What makes our technology unique is the fact that we use cable stays to hold up relatively thin poles as we support what I would call a modified vertical single axis tracker. On this diagram, you can see that this relatively thin pole is supported by these red stabilizing cables, which go through the array diagonally and more or less stay solid for the entire day. Then also there are rotator cables that are attached at the corners of each of the beam, which is at the bottom leading edge of the solution. As you can see, also the lower edge of those diagonal cables are about 9 feet off the ground. We can vary that. We're also pretty tolerant with sort of rolling grassland. And as a result, we can handle a lot of different environments. On the base of the stems that hold up the solar panels, it's a relatively modest, minimal impact footing that's really just holding the pole from sinking into the ground. It is secured through cable anchors, which are also minimal impact, in order to hold it for any uplift and also to resist any side push that may be coming from cows, which is relatively modest compared to the wind demand on these arrays. The panels are also capable of being tipped into a stow position and leaned back essentially if the wind gets too intense, and also leaned forward to shed snow. That happens through our SCADA system, which is connected to the stabilizing cables and is able to draw the panels forward or back depending on what the needs are at the time. The rotator cables and the stabilizing cables in concert are able to hold on to these panels as winds progress. The nice thing about what we've done is you can see in the diagram the hedral truss, which directs most, if not all, of the wind force down to a spot on the initial cable, on the initial pole, which is basically proximal. So as a result, there's very little bending force on these poles, which is what lets us get away with so much less steel as we move forward. We anticipate that we can build at height for about the same amount of steel, if not a little bit less, than ground-based solar, and significantly less steel than some of the higher, more reinforced solutions that we've seen out there, according to our estimates. We also believe that our manufacturing capabilities or our assembly procedures are more efficient than ground-based solar, and there are some other efficiencies that come from that. And of course, it's much better for ground prep because you don't have to have any fencing. There's no leveling that's necessary for putting in these poles. So there's a lot of advantages on how that works. If you can move to the next slide, I will show sort of how the rotating works. So in a series of slides here, what you'll see is the red and the green rotator cables are attached to that first pole, which we call a bloom on the left-hand side. And as we progress, next slide, those are pulled in and then pulled out by winches that are located on these pitch poles assemblies, which are on the surrounding the entire perimeter of the solution. The winches are most active on the south and the north side, which are the ones that take care of the rotating as well as holding on to the panels in extreme wind events. One more slide just to show it clicking all the way over. So what we have here is we think is a pretty solid solution that uses what we would declare as modern bridge technology. Our savings from steel is not really surprising. As you see structures be progressed through their normal engineering life cycle, there are sort of two ways to build a bridge. One is with extra steel for a large truss bridge, or you can move to a suspension or a cable stayed bridge. And there's just a lot of inherent material advantages from using that. I hope there's gonna be time for some questions. I'm gonna put my information in the chat. Also, I want to acknowledge my CEO, Doug Krause, who's also on the call. So any questions, put them in there for us. We look forward to talking to you more. Thank you.
Thanks so much.
Yeah, thanks, David. Next up, we've got Glenn from Soliculture.
Sorry. Yeah, hi, this is Glenn Allers with a Soliculture. In 2015, we introduced to the market the first luminescent commercial scale greenhouse integrated solar panel. This was after 3 years of development working with commercial local greenhouse growers and the universities. Since that time, we've installed solar into commercial greenhouses from California to Boston and into Canada. To date, we've only seen positive responses from the crops grown underneath our panels. This picture, for example, is a half-acre installation that we did in a 15-acre greenhouse in Ontario, Canada. This greenhouse produces organic herbs like basil for the city of Toronto. The power needs of a climate-controlled greenhouse are very high. The power produced by this installation is fully consumed within the greenhouse. So our business model is to offset the greenhouse electricity consumption at retail rates, which greatly improves the ROI relative to selling power to the grid. This array has been in operation for about 4 years now, and it consistently produces about 30% more power than the SDC rating due to reflected light and the luminescent film, which I'll talk about next. Next slide. So our panels use a color shifting technology that comes about from a luminescent pigment that's included inside of the panel. This pigment selectively absorbs the green portion of the solar spectrum and converts it to red light. The red emission has two advantages. First, it improves plant growth. Plants are green for a reason. They don't like green light and they want to reflect it away. Whereas red light has the highest photosynthetic efficiency of any light in the spectrum. Therefore, by increasing the amount of red light, we can increase photosynthesis efficiency without adding additional stress to the plants. In this way, our panels can actually stimulate plant growth. The second advantage of the green to red conversion is that much of the emitted light is captured within the waveguide of the glass plate. The emitted light travels through the glass and is absorbed by embedded solar cells within the panel. This increases the current output of the cells by as much as 30%. In this way, the luminescent pigment enhances both power and plant growth. Sorry about that. This combination of luminescent pigment and solar cells is a basis for what is known as a luminescent solar concentrator. This concept was first developed in the 70s, but was never commercialized until now. We're the first commercial scale luminescent solar concentrator on the market. The panels are semi-transparent with a partial silicon solar coverage of about 20 to 40%. Luminescent pigment is in the area between the cells and captures both transmitted light and reflected light. The panels are manufactured in a tier 1 commercial manufacturing facility using standard production procedures. Next slide. The advantage of combining solar with covered agriculture is that relative to open field agriculture is the increase in resource utilization. For example, lettuce grown in a greenhouse is 100 times greater yield per unit area relative to open field growing. This is because 1, you can grow all year round. 2, the plant density is much higher in a greenhouse. And 3, the time to harvest is much shorter due to the controlled climate. The combination of covered agriculture with hydroponics or drip irrigation further reduces water consumption, which is critically important inside arid regions. For example, in the arid region of southern Spain, there are 125,000 acres of greenhouses. Basically, the entire southern tip of Spain is white due to greenhouses. There have been a number of studies trying to put standard black solar panels into a clear solar panel with a partial coverage. In almost all these cases, yields have dropped as the coverage of PV cells increases due to the loss of light. The combination of a red light enhancing film compensates for any light lost to the PV cells and either maintains or yields or increases the crop yields. Our most recent implementation moves beyond the glass greenhouse to a simple high tunnel. That's what we show here is our panels are basically mounted on top of a ground mounted PV array. We apply a plastic film to the remainder of the array to generate a protected growing space for the crops. We performed trials in this greenhouse for a year, and we saw significantly better growth under our panels relative to the simple plastic covering, which you can see here very obviously just from visually looking at the crops. By combining both solar and covered agriculture, we can increase power production, increase produce production, and increase profits. A win-win-win value proposition. Thank you. And I'll put my contact information in the chat.
Great, thank you. All right, next up, we're going to hear from Thomas DeLu at Agri.
Yeah, hello. I'm Thomas, working for the international business development of Agri. So as you can hear, we are a French company and opening our activities outside of France. But we are already very successful in France with our agrivoltaic solution. So next slide. So our approach is a bit different within agrivoltaics. We start from agriculture and we consider all the challenges that agriculture is facing at the moment related to the climate change. And we try to bring protection to the crops, bringing some shading and some protection against heat waves, frost for the crops using solar panels. So the idea is to keep 100% of the land for farming under the panels and to move the panels with single axis trackers above the crops to share the light between energy production and the needs for the light. So we developed a unique software which modelized the crops growth over the time and the crops needs for light. And based on the information we get from the field from sensors, we change the tilt angle of the panels every minute in accordance with the crops needs, and also in order to maximize the energy production. So our system is completely built up above the crops, usually 15 feet high. It could be more or less, in order to allow the machines and the tractors to work under the panels. So we don't change anything in the way of farming under the panels. With this system, we can share the light usually with 80% of the light given to energy production and 20% of the light given to the crops. But obviously it would depend on the crops needs and the climate and the condition you could have on the field. So next slide. So as I said, the way we work, we start from agriculture, bringing benefits to the crops. And we bring also our expertise to the IPPs and developers in order to develop valuable and profitable projects for agrivoltaics with our solution. But what is important is that we can put a guarantee on the energy production for the IPP based on the calculation we'll do in this sharing of the light between the crops and the energy production. So as I said today, it's a very successful solution we have in France, and we have now 100 megawatt roughly already existing, developed or under construction. It is roughly 50 projects, let's say in France, and you can see here one of our latest project on the peach trees, which is a 2 megawatt size. So you can see picture there. And installation, this one is a bit higher above the trees. We are closer to 20 feet high with this installation. Next slide. So this picture is really very interesting because you can see the actual benefit we bring to the crops and to the farmers with such a solution. So you can see on the top what happened to a vineyard in 2022. It was end of July, between end of July and the harvest time in September. So on the top of the picture, you can see the vineyard and the grapes not protected by solar panels. And you can see the sunburns on the leaves and the burns on the fruits and the fruits that are dried on the right. And under the protection, you can see that, yeah, it's much better for the vines, and the grapes looks much better. And the quality of the wine was also better because we were able to manage the acidity level and the sugar level within the grapes by managing the light in the right period for the fruits. So it means that we really bring benefits to the farmer there, and we share these benefits with the IPP and the power producer with this project in ensuring that enough energy would be produced for the business plan to be profitable, and that the farmer will be convinced by such a solution. So that's actual dual use of the land, but with also a clear dual benefit for the system. Okay, and that's it, yeah.
Well, thank you so much.
Thank you, Kevin. Next up, we have Chris from Taka Solar.
Great. Hi, all. Nice to see you. Sorry if my voice is a little wonky today. It's been a cold season. Yeah, so Taka is trying to develop some novel solar panels, I think, that address some of the issues that our friends like RUTE and Agri are also working on. So hopefully we'll all together come to a really good solution. Next slide. What we're trying to do is make specialized solar panels whose basis is using glass tubes. This is inspired by solar thermal tubes that you see a lot, particularly in Asia, but also the ever-beloved Cylindra where I used to work. And those tubes actually have a bunch of interesting advantages. Now, I should note parenthetically that we think our first real market is actually going to be over parking lots, but AgriSolar is a wonderful follow-on market that we're looking at. So the tubes, if you make them like this, they're aerodynamic, which means that it's much easier to mount them. So you get some of the advantages that RUTE is focusing on the same way, and Agri and other people. But you also get sun tracking out of the tubes because the solar cells face east and west simultaneously. There's no moving parts, but you still get sun tracking behavior. And the third one is it's very easy to space the tubes further or close apart just by where you connect them to the cables. So you can tune the average light level. It's not something that's variable after installation, but you can tune it for a given location and sort of climate. We did some work on next slide for a Department of Energy SBIR grant. I know at least one of our fellow cohort is here today. Hi, Larry, good to see you. So there were 6 of us teams from the 2021 cohort. And I'm sorry to say nobody got a phase 2 award. So the DOE seemed to be really hating on AgriSolar last year. But our studies drew on a system that had been built by Cylindra 12 years ago. And then we added some of our own panels with a wider spacing to sort of map out the spacing density versus crop growth sort of performance. And it worked really well. So you can see the panels there at the left and the different kinds of shade cast on the ground. Our system is the one kind of in the distance with the tubes far apart. This is a view from below and a view from above. And yes, if you think that our panels have wooden beams as part of their structure, you're not seeing things. This was an early SBIR study. We were going to be a little fancier in Arizona and some other places if we'd done a phase 2, but that's going to probably have to wait a couple of years while we develop parking lots first. But what we studied was a couple of different crops like kale and chard and grapes and tomatoes. And we saw some pretty interesting results. So we'll go to the final slide. The sun tracking behavior I alluded to, especially because the tubes are so far apart, was really, really good, better than you would normally get from a one-axis tracker because they don't shade each other until the final minutes of the day. So we think we sort of separated out effects from reduced soiling. The dew would tend to drip the dirt down to the bottom where it was less of a problem. So compared to a flat panel nearby, we got 5% more energy from soiling reductions and 25% more energy from sun tracking, which is a pretty big increase per rated watt. And the thing that we were most gratified by, at least in a sunny, hot place like California's Central Valley, was that we got 50% more kale. And this is obviously a small study, so there's error bars on this. But we got like a lot more crops, just like the folks at Sun Agri have seen. So we know that shading can help, especially in sunny and hot areas. And we were really gratified by this. It's an easy system to build. Now, I don't know what the costs are going to be. We haven't built a system for customers, but we did some techno-economic modeling. And we saw that, if you did a 10-acre kale farm, the increase in production of food plus the electricity, even at a very low, nearly wholesale rate, meant that the farmers get 1.7x the money from their farm over the first 15 years while they're paying off the loan. And after that, they're quadrupling their revenues from the farm because of the extra crop and the extra electricity without any big compromises. This won't apply everywhere, but at least in the Central Valley of California, it seems to be a really exciting thing. Then the real question is, how cheaply can we actually install these? And the interesting thing was, if you sort of do the analysis a different way, it looked like we could support a price closing in on $4 a watt and still be sort of revenue neutral for the first 15 years. So we just have to see if we can actually manufacture them that cheaply. But I would note, our tubes are made with standard silicon cells, standard glass tubes that are made by the billion in Asia, and standard encapsulants. So we think that the panel cost should be reasonable in the long term, but it's yet to be proven. All right, thanks.
Well, thank you so much. Next up, we're going to hear from Jeff Sharp at Stracker Solar.
Greetings, thanks, Stacy and Danielle and everybody. Stracker Solar is an elevated dual axis tracking system. We have produced it starting here in Ashland, Oregon, have 7 years of installations across a variety of climates and terrains. Next slide. The idea of this is a minimum 14-foot ground clearance below. We're robust. We have one of the few trackers that have a UL 3703 listing, patent pending, and a minimum 14-foot ground clearance at all time. Works for typical combines and tractor operations. I was a organic farmer in Montana before coming to do this one. Lots of years of solar industry experience. Next slide. The beauty of it, of course, is dual axis tracking stays perpendicular to the sun all day long. So we get that maximum power generation at all times during the day. These are our Model S1B. They're 12.6 kilowatt units, showing 50% greater energy gain than flat rooftop units, 50% more than optimally tilted and pointed fixed units. Next slide. So our 120 mile an hour wind rating, each batch is load tested to meet the loads that we need to meet. Pole mounting works on up to 40 degrees slopes. We can handle hilly slides. Each unit is independent in that it has its own GPS validated control system. We can put together groups of these, typically in 200 kilowatt blocks, to be able to work off a single anemometer. The ones you see here and the more typical ones are each one has its own anemometer to go into its safe stow position whenever the winds pick up a little bit. And we're seeing that owners are really appreciating the visual representation, kind of the curbside appeal of what's going on with that. Next slide. Robust and reliable, all domestic steel structures. So we're able to do the get the 40% FITC, UL listed, 120 mile an hour wind, 30-year structural and PV warranties. In our minimal maintenance, we have a total of 8 points for greasing. There's 2 large slew drives, one for each axis of rotation. That's a simple annual 30-minute maintenance plan, plus looking at it visually. And I guess that's what I got. Is there another slide?
There is not.
Okay. I guess I'll add, we're sitting at about 350 a watt right now. That's about equivalent to 230 a watt on fixed because of the extra power we're producing. And also our analysis have shown that we have about 65% lower carbon footprint per kilowatt hour produced, primarily because of the more power that we're getting maximum power from each PV module. And in all of these systems, we're seeing the modules are by far the biggest carbon footprint.
Great.
Thanks.
That leads perfectly into our follow-up question, which is, if we could go around the room in the order you all spoke, could you all speak to the cost of this? Is it similar? Does it compare? Is it more? What are you seeing for costs? And I think we'll start with Ian Score from Sandbox. We can't hear you, Ian.
There we go.
There you go.
Can you repeat the question one more time?
I just was hoping everyone could speak to cost, because that's the main question we get. Does this cost more or less same as a regular or a standard solar installation?
Yeah, the cost of the structure we installed here was about $4.35 a watt. So that's pretty comparable to today's ground mount standards on a residential scale. So again, this was a 15 kilowatt system. And the payback is looking pretty strong with utility rates here. Of course, that varies based off your local utility. Based off utility incentives and local incentives, the payback here is going to be about 6 or 7 years, which for Colorado small commercial is really empowering.
Yeah, that's amazing. Anything less than 10 is great. Jake, what are you seeing?
Yeah, so the racking that I demonstrated is not cost efficient by today's standard. What we're using today is more commercially available products. That's not to say that there are a lot of lessons learned from what we installed at the 3 sites that I showed. RBI, for example, has a product that's pretty comparable if you just design specific to that. Those costs are I guess a percentage, 20%, maybe higher, especially as the higher you go with these systems, elevating them. But in Massachusetts specifically, there's an incentive within the solar program here in the state, which incentivizes agrivoltaics, and they're seeing a similar payback timeline, as Ian mentioned, sort of that 6-year time range. And the IRA makes it even more capable to do agrivoltaics, higher ITC, including the interconnection cost in the ITC payment as well. So can get creative with financing to make these projects work.
Great, thanks. James, what are you seeing with Helical?
So in sort of a low quantity 30-piece build today, given the inflation that we have on steel that's come down, but still got a ways to go, we're looking around $3.11 per watt, equivalent to when you compare us to like a rooftop. So that would be $3.11. And we would expect that to go down over time with quantities using economies of scale. And also, if we were to partner with sort of a larger manufacturer or something like that, we could definitely see some more price decrease in that going forward.
Great, thank you. Tim, what do you guys see at Sunstall?
So the pricing for the vertical racking is also comparable. The only thing you need to consider is that, yeah, you have a lot of posts, because every module is held by 2 posts. But then on the other hand, you can choose which module you want to use. So the system works with different kinds of modules. You can use 350 watt modules, you can use 600 watt modules. So the price per watt can go down if you use bigger modules.
Great, thank you. David, what are you seeing for costs in your design? Or
So
are you-
RUTE was really designed for large scale deployments. We're looking at rangeland, so not some of the smaller installations. We think at scale, which we would define as about a 4.5 megawatt block, we are comparable to a ground-based HSAT trackers at the present time. If you go smaller, the prices go up. The rendering I showed you earlier was for a 1.5 megawatt system, and we're looking at, even at that size, about $2 a watt. And we're just not as susceptible to some of the steel issues as well. So that really makes things a little bit more solid when contractors are trying to price things out.
Great, thank you. Glenn, did you want to speak at all? I know you did a little already.
Yeah, so if you don't consider, if you consider the panels as just an incremental cost over the cost of the greenhouse, then we're extremely competitive. We're probably less than $2 per watt, especially relative to building a solar array next to the greenhouse. So by integrating into the greenhouse, we also qualify for a lot of incentives that actually makes the panels come in for free. And that gives you really good ROI. So just considering the incremental cost of the panels in the greenhouse, we're below $2 a watt and very competitive.
Wow, and so are those incentives your utility incentives, or are they state incentives?
Most federal incentives, both the USDA is now being very generous with incentives, as well as the standard tax credit. The big advantage is that you can apply the tax credits to the entire structure, not just the panels.
Oh,
And
interesting.
that's what ends up paying for the panels.
Great, great, thank you. Thomas, what do you see for costs with Sunagri?
Yeah, so the solution we propose is an elevated supporting structure. So the main difference compared to ground mount power plants, the additional steel you need to elevate the structure. So it's highly dependent on the height you would have for the supporting structure. Usually what we can see is an additional cost there, which is roughly between 20 and 30% compared to a similar ground mount power plant. But that's really important not to make unfair comparison there, because we speak about agrivoltaics. So it means that we don't bring only green energy there. We bring another thing, which is benefits to the farmers and to agriculture. So additional revenue or protection on the crops or things like that. So we have to be a little bit careful with such a comparison regarding traditional power plants on a rooftop or ground mount and such agrivoltaic solutions, which are more combined approach there. And also, as Glenn said, there are at the moment in the US many ways to get some additional money from support, from incentives, or also from you can avoid in some areas some mitigation fees to use the land, things like that. So there are many ways to compensate this spread between the cost in such solutions also.
I agree, yes, and we have a whole funding map that can help folks if they want to look on our clearinghouse.
Yeah.
Okay, Chris, did you want to speak at all to costs from Taka's?
Yeah,
I
I mean, I sort of mentioned it before. We're early enough that we don't have any hard numbers. I would just say that, as I mentioned before, I think both Sunagri and RUTE are sort of the leaders on thinking about these kinds of questions in the way that we think about them, trying to take advantage of tensile members as a key element and trying to, sort of just get the solar tracking benefit that both benefits plants and the crops. We have reason to think we can get it down to $2 a watt. But, you see numbers for Jack's Solar Garden, which are all over the place. But in theory, you should be able to do that at large scale, same as any other one-axis tracker for around $1. We're not going to be competitive with that. But as Tomas mentioned, you're producing more crops, like you're actually benefiting the crops, not trading off for them. So that's a major source of revenue for the farmers, which can support the somewhat higher costs that we have. And I think that applies to a lot of the folks here. But if I were to try to give a number, it would be very disingenuous at this point. We're not far enough along.
Great, thank you. And Jeff, I know you also spoke, but do you have anything else you'd like to add?
Just add a couple things. So I'll reiterate, we're about 350 a watt turnkey installed. That's equivalent from the extra power that we produce. That would be equivalent to about $2.30 on a fixed system. We're also exploring ways to reduce those costs by using a driven pile foundation system for both our foundation and our pole. And I'd also note that the continued use of the ground below, the fact that if you put these over parking lots, over farm ground, you don't have to put any fencing up, you don't lose any of that. If there's any value on that land, that gives us another really value add. Thanks.
That's great, thank you. So I'd like to thank all of our presenters. We're coming to the top of the hour. If you haven't already, could you drop your contact information into the chat so attendees can follow up with you if they have questions? We will have this posted within around a week. And then if you have any questions for us later or want contact information, you can always email us at agrisolar@ncat.org.
Yeah, thank you for all of our participants for joining. This was a very informative hour. So everyone that presented, like blown away by your research and what you developed. Just great, great stuff.
Yes, good job, everybody.
Yeah,
Thank you. Thanks all.
Thank you.
thank you guys all.
Okay, we'll stay on a couple minutes to let everybody drop their emails into the chat. And if we haven't seen you yet, we'd love to come tour. So to all of our presenters, we're coming your way.
Yeah.
We'll be in California next week, or actually April 4th and 5th, if anybody wants to go on the tour. We'll be going from San Luis Obispo, from the Gold Tree site to Topaz. Those are solar grazing tours, and we will have a live webinar with Sita Sisla talking about soil health and impacts from grazing. And then the next day we'll be with Ryan Indart and Indart Grazing in Lemoore, California, at some large scale arrays there. So
Yeah, great.
we encourage you all to come. These are free. They're a lot of fun. So
If you go to
please join
our,
us.
yeah, please join us. If you go to our events page, you can sign up. There's still lots of tickets left. We really want you to join, and we'd love to meet everyone in person if you can be there. So
Okay, thanks. Oh, looking forward to seeing you then, Tony.
yeah.
Okay, looks like folks are starting to drop off. Great. All right, thank you. Nice to see you all.